Let us begin. So, I'm on page 170. Continuing from yesterday. Okay?
Yes.
She'll take it as well.
And you see the BP, right? That's 30%.
30 test 1, 70 test 2. So your test 2 actually, for a lot of you, it really boosted your DP because if you like you did a little bit bad in the first test, your test 2 saved you because 70% is a lot. Right? So it actually added up a lot.
So you add them together and you divide it by 4.
No, 30% of test 1, 70% of test 2 is there. It will give you a number. Okay, so yesterday we looked at expansion of solids. Right? We've looked at the expansion of solids, we've done linear, area and volume. Okay, remember we spoke about the coefficients. Okay, so now I'm on page 170 where I'm looking at volumetric expansion of liquids. So yesterday we looked at how heat would affect a solid. Remember, if heat is added to the solid, it will start to expand, right? So your length, area and volume will get bigger. If heat is removed, it's going to contract. So your length, area and volume will get smaller. So that's for solids. Let's look at liquids. So, because liquids and gases take the shape of the container, only their change in volume can be examined because it's dependent on what volume it's in, like what type of container, whether it's a square container, round container, that sort of thing. When a liquid expands because of a change in temperature, the container's temperature will also change and it will also expand. Okay? Absolute and apparent expansion. So the expansion of a liquid can be illustrated by means of a flask with a rubber bung and a glass tubing as shown in figure 7.11. Okay? So they tell you fill the flask with water and press the bung until the water rises in the glass tube. If you put the flask in hot water and heat it, the water level in the okay, don't worry about that, right? They just give you an experiment, right? I'm at the part where they say the apparent expansion. So the apparent expansion coefficient of a liquid is the amount by which the liquid expands per degree rise in temperature, irrespective of whether the container itself has expanded or not. Okay? So whether the container expanded or not, your liquid will still expand in the container. Okay? So let's do example 7.9. Okay? So example 7.9 and also the formulas. So the only formula you'll concern yourself with here is the volumetric formula. Now we said change in volume is equal to your coefficient of cubic expansion or volume expansion times initial volume times the change in temperature. Okay, because remember with liquids we only worry about volume. Okay, so this is what they tell you, right? For example 7.9. So they tell you that a glass is filled with 35 centimeter cube mercury. So the volume of this mercury is equal to 35 centimeter cube at a temperature of 20 degrees Celsius. The temperature is increased to 50 degrees Celsius and the linear expansion coefficient of glass, so the glass tube that it's in is 9 times 10 to the minus 6 per degree Celsius, and the volumetric expansion of mercury is 17 times 10 to the minus 5 per degree Celsius. Calculate the volume that will overflow. What do you think, guys?
Expansion.
How much of mercury will spill out of this glass when heat is added? Right? So how would you work that out?
Let's work upon the volumes and subtract the one from the container.
You need to
So you actually need to work out, right? You'll need to work out the change in volume of mercury. Because when heat is added, how much did that volume increase by? Because remember that volume of 35 centimeter cubed is in a glass container which is also 35 centimeter cubed, right? If just say this is it, right? That's your glass, right? Inside here is your horrible writing, right? But this is 35 centimeter cubed. It's full inside. Now what's going to happen when heat is added? This glass is going to expand, and the mercury inside is going to rise. But they're not going to expand and rise at the same amount. Your glass may expand a bit, but your liquid level may rise more, which will cause it to obviously overflow. Because now just say if this glass expanded to about 37 centimeter cubed, right? So now you can hold 37 centimeter cubed. But the mercury expanded to 39 centimeter cubed. 2 centimeter cube of volume is going to obviously overflow because it's not going to be contained in the container. Yes? So what we need to do is work out the change in volume for mercury, the change in volume for glass, and then subtract it, and that will give you the amount that would have overflowed. Obviously, we're expecting the change in mercury to be higher than the change in glass. Okay? So let's start, right? So, your change in, so for mercury, you understand the concept of what I'm saying, right?
Yeah.
Okay, so your change in volume for mercury is equal to your cubic coefficient of mercury multiplied by your initial volume multiplied by a change in temperature. Okay, this is all in degrees Celsius, so that's fine. Our volume is going to come out in centimeter cubed. Understand that, right? So, this is 17 times 10 to the minus 5 times 35 times 50 minus 20, which is 0.1785 centimeter cubed. So this is how much the volume increased by. Okay? Now, let's look at the glass. We want to calculate the change in volume for glass, which will be the cubic coefficient of glass multiplied by the initial volume multiplied by the change in temperature. Right? Can we work it out? Based on the information given, can we work it out?
What do you mean? Yeah.
Yeah. How?
We don't know.
No, we don't.
We don't have
We have
the coefficient,
got the
the cubic expansion, that's times 3.
So,
So that
we need to take this
plus whatever.
and work out this, right?
Yeah.
So remember, so this is for the glass, right? Your cubic coefficient of the glass will be equal to 3 times your linear coefficient of expansion for glass, right? Yesterday we did this, right? So this is 3 times 9 times 10 to the minus 6, which is 27 times 10 to the minus 6 per degree Celsius. Now remember this from yesterday, right?
Yeah.
So taking this,
No, it's very clear that they put together like this.
yeah. So you get 27 times 10 to the minus 6. Your initial volume is 35. Your change in temperature is 50 minus 20, which is
0.0284.
okay. So now we know how much that volume changed for the glass. We know how much the volume changed for the mercury. So, can I write it here? Your volume that overflowed will be equal to your change in volume for the mercury minus your change in volume for your glass, which is 0.1785 minus 0.0284, which is
0.1501.
so that's the volume of mercury that overflowed when the temperature was changed to 50 degrees. Do you understand what's going on? Yeah? Okay, is anybody confused? Okay. Okay, so you can. Okay, yeah. So that was expansion. Go and answer the question. Last chance. Yeah, right. Okay. So I'm on the anomalous expansion of water. So not all substances expand when it is heated. For example, water during certain temperature ranges contracts if it is heated. Okay, this is known as the anomaly in the expansion of water. I'm not going to go through that example they gave you. I just want you to look at the graph. Right? Remember, we've been saying that liquids will expand when it is heated. Right? But if you look at from negative 20 degrees as it's going up, it reaches a certain temperature where your volume starts to decrease as your temperature increases. Okay? And at a certain point, after 4 degrees, it carries on as normal. That's known as the anomaly of water. Right? Where they tell you at 4 degrees, a fixed mass of water will have its minimum volume and its maximum density. Okay? At 0 degrees, ice is formed and a sudden increase in volume will take place. Remember yesterday you asked me when we were freezing water, how come it expands? So if you look at your graph backwards, right? Like if you start from 100 degrees and you go. Right? So if you start from 100 degrees going down towards 0, you can see your volume starts to decrease. But when you come around the temperature of 4 degrees, that's usually at like 0 degrees is where ice will start to freeze. So 4 degrees is like generally ice. You can see how the volume increases for a certain amount. Okay, so like till about maybe let's say 8 degrees or something like that. And then after that it continues until 20. That's the anomaly of water. Water is like the one substance where at a certain temperature range, its volume thing flips. Okay, so yeah, it's just nice to make a note of that. But yeah, so for volumetric expansion of liquids, it's just that you need to know when it is heated, it will expand, but not for all liquids, because remember water is different. Okay, you'll follow the same formula. Change in volume is equal to your coefficient of cubic expansion multiplied by your initial volume multiplied by your change in temperature. Okay, is everybody okay there?
But there's no questions that were asked about that kind of stuff.
They probably may ask you a theory question or something. Okay, so you will just go through some past papers and see if they do mention it, because the only thing they can ask you is theory questions on them. Okay, now I'm going to move on to the last part of engineering science and 4. Okay, I'm looking at the laws of Boyle and Charles and the characteristic gas equation. Has any of you ever seen Boyle's Charles law? P1 V1 is equal to P2 V2. Okay, very simple formula, right? I'm going to go through it now. So remember we looked at the expansion of solids, right? Where what we did yesterday. Then now we just looked at the expansion of liquids. And now there's one more type of substance we need to look at, which is the expansion of gas. So that's where we are. So the coefficient of expansion of gases differs from that of solids and liquids in the following respects. All gases have the same coefficient of expansion, namely 1 over 273 of the original volume at 0 degrees per degree Celsius. So basically, all gases have the same coefficient of expansion. The expansion of the gas is relatively large in comparison with that of solids and liquids because of the way the particles bonds are. Okay, it's dispersed. Okay, all gases obey 3 laws that relate volume to pressure and temperature, namely Boyle's law, Charles' law, and the pressure law. Okay, so the first thing is Boyle's law. Can I take this up? Okay, very simple formula, guys. Don't worry. You took a question?
No.
That's okay.
Okay.
Okay, so Boyle's law at the top, please highlight this next part because that's the definition of Boyle's law. They may ask you, okay? Boyle's law states that the volume of a given mass of gas is inversely proportional to the pressure to which it is subjected if the temperature remains constant. So Boyle's law says that the volume of a gas is inversely proportional to the pressure of a gas if temperature remains constant. So what does that mean? If your volume increases, your pressure decreases. If your pressure increases, your volume decreases for gases. Okay? So in doing that, Boyle came up with this law which says that P1 V1 is equal to P2 V2 at a when temperature is constant. Okay, that's Boyle's law. Okay, definition told you about it. Okay, so Charles' law. So Charles' law says that this law states that the volume of a given mass of gas changes by a fraction of 1 over 273 of its volume at 0 degrees for each Celsius degree rise in temperature if pressure remains constant. The volume of a given mass of a gas at constant pressure is directly proportional to its thermodynamic temperature, where T is the thermodynamic temperature in Kelvin. Okay, so there, the second point, that's what you'll highlight as the definition. Okay, at constant pressure, the volume is directly proportional to temperature. And he came up with this formula. Temperature must be in Kelvin, right? Okay. So, the combination of Boyle's and Charles' law. So consider a gas with a volume of V1 at a thermodynamic temperature T1 and at a pressure P1. Okay? So you can see nothing is kept constant, right? If temperature is kept constant while the pressure increases to P2, then the volume will change to V, and then they made something for Boyle's law. Then according to Charles' law, they show you something else, and then they come up with the general gas equation. Okay? I don't need to give you all this deliberately because they're not going to ask you them. Don't unnecessarily, right? So, they came up with the general gas equation, which says that P1 V1 over T1 is equal to P2 V2 over T2. Okay, this is it. It's basically like a combination of Boyle's law and Charles' law. Okay, and then sometimes they say that P V over T is equal to a constant. Okay. All will be so far, right?
Yes.
Okay. So let's look at it in an example. So, example 7.10. So example 7.10 says that the volume of a gas is equal to 40 centimeters cubed and a temperature of 30 degrees Celsius. V1, T1. Okay? Then they tell you calculate the volume, so they want to know V2 at T2 of 60 degrees Celsius if pressure is constant. So how would you do that? Charles' law, right? Because Charles' law states that if your pressure is constant, your volume is directly proportional to your temperature. Okay? So, what do we also need to do? We need to convert this to Kelvin, because remember with Charles' law, well, for all these laws, your temperature needs to be in Kelvin. Okay? So, this here will come out to, how you convert to Kelvin? At 273. So that's our temperatures in Kelvin. So using Charles' law, which says that V1 over T1 is equal to V2 over T2. If I make V2 the subject of the formula, I'm left with V1 T2 all over T1, which is 40 times 333 all over, which is 33. 43.
43.960.
Do you understand what I did, guys? Basically, yeah, we should just show to these three laws, and then they gave you a question where pressure was constant, so you have to look at Charles' law. They want to know volume, you just substitute it and solve it. Okay? Let's do another example, right? Example 7.11. So example 7.11 says that a volume of gas is 20 centimeters cubed with a pressure of 0.2 MPa, right? Calculate its volume, they want to know V2. If, calculate its volume at 0.098 MPa and the temperature remains constant. So if the temperature remains constant, which formula would you look at? Boyle's law, right? So remember this here is equal to 0.2 times 10 to the 6 pascals, right? And this here is equal to 0.098 times 10 to the 6 pascals. So Boyle's law says that P1, P1 V1 is equal to P2 V2. We know V1, we know P1, we know P2, we can solve for V2. So P1 is 0.2 times 10 to the 6. Your volume is 20, equal to P2, which is 0.098 times 10 to the 6 times V2. So your V2 value is 0.816 centimeters. That's your V2. Not bad. Not bad. Okay. Can I check out the small packet? This one. That's it. I have no way for it. Oh. Details, are you?
Yeah.
Okay, so example 7.12. The volume of a given mass of gas at 30 degrees Celsius and a pressure of 0.2 times 10 to the 6 pascals with a volume of 40 meter cubed. Calculate the volume of the gas, so they want to know V2, given that you know T2 is equal to minus 12 degrees Celsius, and P2, which is 0.6 times 10 to the 5 pascals. Right? That's the information they gave you. So, looking at the information they gave you, we can see that temperature is not constant, because your temperature just changed. Your pressure is not constant, because your pressure just changed. So, you're going to have to use your general gas equation. So, before we do that, let's convert this to Kelvin. So, this will be 303 Kelvin. And if you add 273 to negative 12, you get 263. Right? You all agree? So your general gas equation says that P1 V1 over T1 is equal to P2 V2 over T2. Right? Substitute your values into it. 0.2 times 10 to the 6 times V, which is 40, over T1, which is 263, equals 261. And you all said yeah before. And then P2 is 0.6 times 10 to the, this is not also, this is 3 of 3. T1. Right? 0.6 times 10 to the 5 times V2 all over T2, which is 261. So you solve this, multiply by 261, and then divide by 0.6 times 10 to the 5. Right? So you get a value for V2 being. Can you understand what I did, right? It's just I took the information that you gave me, and then I saw which formula I could use, and then I used the formula. One 114.85 centimeters cubed. Meters cubed. I've lost one mark. Some of you know that. Swedish. Kinda you too. You too. Everyone here. Everyone here. At some point, somewhere in the paper, you lost mark for units.
Me?
Hey, yeah, I'm telling you something. You never you lost somewhere else.
No, number 6, I know. Number 6, it's high.
Okay, guys, so gas is not bad.
It seems,
There's one more equation we need to do, and then
it seems easy.
done. We're done with the whole semester. Okay, not the whole semester, just the exam part. Then we're done with the whole semester. Come a long way.
Seems easy now.
Come in, you ready?
Ready.
Oh. So, I'm on page 177, right? The general character. Just take a minute to look at this board. Let's come back there. The general and characteristic gas equations. So, for the combined laws of Boyle and Charles, PV over T is equal to a constant, which we said over there, right? Okay. This constant differs from gas to gas and is called the gas constant, and it's known as R. So for 1 kg of gas, PV over T is equal to R. That R is a constant, right? For 1 kg of gas, PV over T is equal to the constant. That constant is known as R. So for a mass of whatever kg of gas, PV over T is equal to mR. And they come up with this formula, PV is equal to mRT. This equation is called the characteristic gas equation. Highlight that, asterisk it to everything. It's a very important equation. Okay? Also take note of the units of everything that you are using. The units for your pressure needs to be in pascals. The units of your volume needs to be in meter cubed. Your units of your...
What time can they know?
What's the time?
It's 12 now. Can they know? Or do they need to just start say 15 now and then knock off it?
No, I think Yeah, but blend rate will come. 3 more blend rate will come now. Okay, then they usually do the assessment.
Yeah.
And the ones that only see 13 workbook, they usually give it to me today. Because they never get last week. Thanks, Yoga. Right. Your mass must be measured in kgs. Your R is in joules per kg per Kelvin. Okay? Per kg per Kelvin. So that's why you need your mass in kgs and you need your temperature in Kelvin so that it's able to cancel. Okay? And then, yeah. Okay? And they give you the specific gas constant for air, as an example, is 287 joules per kg per Kelvin. So that's the one more formula I want you to know. PV is equal to MRT. Get used to the units that you should have your stuff in. Okay? So when you're solving your answer, you know what units you're solving it to. They give you a summary of the important formula for gases. Boyle's law, Charles' law, the combined law, characteristic gas equation. You're all worked at where you all worked. So you'll know what's STP, right? Standard temperature pressure. Okay. So let's do example 7.13. I can take out this, right? So they tell you the volume of a given mass of gas at 120. So this is example. So they give you the temperature at 120 degrees Celsius. They give you the pressure at 600 kPa. They give you the volume at 0.55 meters cubed. They give you the gas constant of 287 joules per kg per Kelvin, and they want you to solve for M. Okay? So which formula would you use? PV is equal to MRT. What you need to do first? Put everything in the right units. Okay? So temperature is supposed to be in Kelvin. So this is 393 Kelvin. This is 600,000. Not Pascals. Pascals. Volume must be in meter cubed. Meter cubed, right? R must be in joules per kg per Kelvin, so the units of mass will come out in kg. Okay? So P is 600,000. V is 0.55. We're solving for M. R is 287. KT is 393. So your value of the mass comes out to 2.926. And that is the mass of gas that was used. Okay? Ladies and gentlemen, that brings us to the end of module 7. If we turn onto the next page, they give you on the next page, the page 181, they give you a summary of everything we covered there. We looked at converting degrees to Kelvin, Kelvin to degrees Celsius, right? We've looked at the equation for linear expansion, for area expansion, and for cubic expansion. We looked at how you get your area coefficient, how you get your cubic coefficient. Liquids expanding in the flask, we spoke about that. We've spoken about the graph for the anomaly of water. Looked at Boyle's law, which is P1 V1 is equal to P2 V2. We've looked at Charles' law, which is V1 over T1 is equal to V2 over T2 if pressure is constant. Right? We've looked at the combination, which is P1 V1 over T1 is equal to P2 V2 over T2. And we looked at the general and characteristic gas equation, which says that PV is equal to MRT. And you see 182 has the answers to all the modules, which means what? We are at the end, the textbook. Which means that we have just completed syllabus for engineering science. 2 months later, or just under 2 months later, we did it. Any questions on what we covered today? Not bad, right? Very easy formulas to work with. Very straightforward. Okay? So heat in the paper you should get for army master heat. 15.
Yeah, the point is split like equally with all the sections.
Okay, get that full 15 guys. Like, seriously, I mean, looking at what we did.
It doesn't get more complicated than this.
No. Probably the way they ask you the question may seem confusing, but you just need to know how to pull out which is B1, T1, P2, I mean P1, and then which is your other stuff, what they're looking for, and then you solve.
Yeah.
Next, another way they can catch you is they'll tell you a volume of a gas is at 3 kPa, right? Is at 3 kPa and the volume is 0.5 meter cubed. It has a temperature of 280 Kelvin. Okay? Then they tell you that this pressure is increased to 1, I forgot what numbers I used. Okay, let's use those numbers, right? Say that they gave you the volume of a certain gas is at 0.55 meter cubed at a pressure of 600 kPa and a temperature of 120 degrees Celsius. Calculate the volume when your pressure is increased to 800 kPa and a temperature of 120 degrees Celsius. Now, what was the catch? The catch is that the temperature is constant. It's 120 degrees for both. So you just needed to use Boyle's law, which is P1 V1 is equal to P2 V2 to solve. And the only way you'll be able to identify that is if you actually write it down. Because when you write it down, you'll have P1 V1 T1. T1 is 120. You'll write on the other side. You're working on V2, you write down P2, and you see T2 is also 120. If it's equal, it means that it's constant. Yeah? T1 is equal to T2, which is equal to T, the constant temperature. And then you just do it. That's all. That's the ways in which you can. But you'll see when you do past your papers.
Whether you use that the one with the P1 V1 over T1, or whether you just use the P.
You would have still got the same answer because that's temperature. Because the formula would have came to the same thing, right? Another thing you'll see when we start doing past your papers is that see these values for R. Remember yesterday I told you all they'll give you the cubic. For some questions they may give you the coefficients. And on a table, what do you call it, table? Data sheet or something, right? Or formula sheet, or constant sheet, right? They'll give you the constants for what maybe your gravity must be at, like whether it's 9.8 or 9.81. They'll give you these expansions for whichever questions it works towards. They'll give you the constants for R of certain gases. Like you'll see, the question will have maybe air and another gas, I can't think of gases. Nitrogen, right? The question will have oxygen and nitrogen, right? And they ask you to solve for the mass of nitrogen. The R that you will take will be the R for nitrogen. You'll see when you read past your papers, right? But it's not difficult stuff. So guys, we have come a long way. We have started with kinematics at the start with relative velocity, resultant velocity. We've done vertical projectile motions there. Then we went on to angular motion, right? We looked at a lot of stuff in angular motion. We went on to dynamics with Newton's laws and potential energy and kinetic energy. We went on to statics with beams and centroids and bending moments and shear force and everything. Then we went on to skip a module. No. Did I skip a module? Did I? Then we went on to stress, strain, and Young's modulus. And then we came to heat. Okay? Oh, hydraulics we did somewhere in between too. After statics we did hydraulics, then we did stress, strain, and Young's modulus, and then we did heat. We've done a lot.
So tomorrow we're doing the past paper.
Past years. So if you are going to do work tonight, work on preferably last trimester's paper. So when you go on the TVET app, 2023, that paper. There's only one paper there, right? Because these papers never come out yet. So try to work on that paper for maths and science, because that's what we'll be looking at tomorrow. Okay, that's it, guys. See you all if you have exams. I'm joking, I'm not gonna say. So I will see you all tomorrow for class. Past year papers. The last recording on lectures will be posted today. But I'll record the past year papers, but I'll call it something. I'll say like revision past year paper 2023 semester or something like that. Yeah? But all your videos are on the playlist. The playlists are posted into the group. So you'll get access to all the videos. Everything has headings, everything has descriptions of what's in the videos. So it will cover everything that we discussed. So if you just need to access videos, it's fine. Anybody has any questions on anything? Maths, science, related, anything? Cool. Now it's just your. You say that.
Yeah.